We're going to cover titration in our last session for syllabus coverage. This is the part from chapter 8, acids, bases, and salts, that I left for later. So let's cover the technique first from the text, and then we'll do solving on the whiteboard.
Okay.
Just remember, I haven't shared screen. There you are. You see the book?
Yeah.
Okay. So you've seen earlier on page 122, right, in this chapter, that it was possible to prepare a soluble salt by reacting an acid with a soluble base, also called an alkali, and this was a neutralization reaction. And this method, the method used was that of titration. Titration can also be used to find concentrations of the alkali used, right? So it's not just neutralization to make the salt. It is also if one of the concentrations, either the acid or the alkali, is unknown. If both are unknown, then you really can't do anything about it, right? So if one is known and the other is unknown, and then this is where moles come in, right? That is why I left it for later. So now that we are familiar with moles, we can deal with this. So in the laboratory, the titration of hydrochloric acid with sodium hydroxide is carried out in the following way. The 25 centimeter cube of sodium hydroxide solution is pipetted into a conical flask. So the alkali normally goes via pipette into a conical flask, right? Or a beaker perhaps, but conical flask normally. And the acid goes into the burette. A few drops of thymophthalene indicator have been added. It is blue in alkaline conditions but colorless in acid. Right, so when the color change starts, when it goes from blue to colorless, right, that is the neutralization point, right? And you have to be slow while adding. So step 2 is you add 0.1 mole per decimeter cube solution of hydrochloric acid into a burette using a filter funnel, and it is filled up to the 0 mark. Remember, for the burette, the marking starts from the top. You have to fill it from the bottom all the way up to the top till the 0 mark. The meniscus of the liquid should be at 0, right? Depending on what kind of liquid it is, if it's the upper meniscus or the lower meniscus, right? It should be at the 0 mark, right? Once you filled it up, you remove the filter funnel. And in this case, you note that they've given you the concentration for the sodium hydroxide. It was only the volume, not the concentration. So with this titration, we'll be finding out the concentration of sodium hydroxide. Right,
Okay.
the filter funnel is removed. The hydrochloric is added to the sodium hydroxide solution in small quantities, usually no more than 0.5 centimeter cube at a time. So we don't know what the concentration of sodium hydroxide is. If you add a lot of it in one go, you might reach neutralization, the color will change, but you don't really know at what point. You need to be exact, right? Because the concentration, to figure out the concentration, you need exact values of volume. So you need to be slow initially. Right, so you're adding it slowly, 0.5 centimeter cube, half an ml at a time. The contents of the flask must be swirled so that the acid mixes throughout the alkali, right? So this thorough mixing. The acid is added until the alkali has been neutralized completely. This is shown by the blue color of the indicator. Just as it goes colorless, stop. Then you take the final reading from the top, right? So it starts from 0 at the top, and so wherever it is, this is, they're actually filling this. So for example, this, right, you didn't need to use a lot. Maybe you use 5 ml, like 5 centimeter cube. Maybe it's 10, whatever it is. So you take the reading from the top, you go down, you see where the liquid is after the titration. The final reading on the burette at the end point is recorded and further tight. So now you know, for example, it took you, for example, 15 centimeter. I'm saying we're going to do the calculation, but just saying 15 centimeter cube of the acid, right? So the next time you do it, you're going to, you can add like a 14 centimeter cube of the acid just like that, right? This is what we used to do way back when. we could do that, just add 14 centimeter cube or 13 to be safe. Let's say 13. And then after 13, you add it slowly. You should get 15 or plus minus like 0.1 like that. So 14.9, 15.1, maybe 14
Yeah.
point, maybe 14.8 and 15.2, right? Maybe, but right. So, it says over here that uh, the final reading on the burette is recorded and further titrations are carried out until consistent results are obtained within 0.1 centimeter cube of each other, right? And some data samples are shown to the right. So it's over here, right? Volume of sodium hydroxide is 25 centimeter cube. Average volume, so the concentration of the hydrochloric acid is 0.1 mole per decimeter cube. And the volume of hydrochloric acid that you required for the neutralization was 21. So I said 15, that you're doing 21 centimeter cube. So to do the calculations and to explain it, I'm moving to the whiteboard.
Okay.
Right, so you see that there.
Yeah.
And so the data that we have, you can see I've already put in the heading to save those 2 seconds of time that we need. And so you have hydrochloric acid, which is 0.1 mole per decimeter cube, which is how you give concentrations for solutions. And you use 21 centimeter cube of that one. And then you had sodium hydroxide, which the concentration is unknown, and you took 25 centimeter cube. Okay, so one thing you need to know is, like, you need to write out the balanced equation. So HCl plus NaOH will give you NaCl and H2. So this in itself is balanced, right? You obviously write the state. So these guys are aqueous. This is a liquid, and the mole ratio is 1:1 throughout. Right? Then you, because you have 21 centimeter cube of hydrochloric acid, you can get the number of moles, right? Which is volume, right, in dm cube times the concentration. So that would be 21. I hope you're following along.
Yes.
Divide by 1000, so that will give you dm cube multiplied by 0.1. And so the number of moles of hydrochloric acid that you used were 21
Zero. Okay.
or 2.1, sorry. No, 21. They're giving
Yeah.
21. Okay. 21 into 10 to the power minus 3. Okay. Or 2.1 into 10 to the power minus 4. If you want to write it that way, you can also do it that. Right? 2.1 into 10 to the power minus 4. That's the number of moles that you have. So that's the number of moles that you used for hydrochloric acid. Okay. To
Yeah.
neutralize, so because the mole ratio is 1:1, that means 1 mole of sodium hydroxide will react with 1 mole of 1 mole of hydrochloric acid will react with 1 mole of sodium hydroxide, and that means 21 into 10 to the power minus 3 moles of hydrochloric acid will react with 21 into 10 to the power minus 3 moles of sodium hydroxide, which means the 25 centimeter cube of NaOH that you used had 21 into 10 to the power minus 3 moles. Does this make sense?
Yes.
Are you sure?
Yes.
Can you explain that again?
Right. So we first found the number of moles of hydrochloric acid that were present in the volume of hydrochloric acid that was required to neutralize 25 centimeter cube of sodium hydroxide. Right. And so 21 centimeter cube of hydrochloric acid was used to neutralize 25 centimeter cube of sodium hydroxide. We have the concentration of hydrochloric acid, right? And using that information, we found the number of moles of hydrochloric acid that were used, which is 21 into 10 to the power minus 3. Then the reason we got the balanced equation is so that we could take the mole ratio. And so what we're concerned with is the mole ratio between hydrochloric acid and sodium hydroxide. We're not concerned with the products in this case. And so the mole ratio between these two guys is 1:1, which means 1 mole of hydrochloric acid will react with 1 mole of sodium hydroxide, which means that if you had 21 into 10 to the power minus 3 moles of hydrochloric acid, those will react with the same number of moles of sodium hydroxide, which means that you had 25 centimeter cube of sodium hydroxide, which contained 21 into 10 to the power minus 3 moles, because the ratio of moles, even though the volume is different, the number of moles is the same. So we have the volume, we have the moles. Can we find the concentration? Yes, we can. Right? And so the concentration, remember the formula for concentration?
Yeah. Uh, Moles divided by volume.
Yes, moles upon volume in decimeter cube. Right? And so for NaOH, you've got 21 into 10 to the power minus 3 divided by 25 into 10 to the power minus 3.
We got 25 multiplied
That
by
is
10.
that's 25 divided by 1,000, so that's in decimeter cube,
Okay.
right? And so what you get is, what do you get? 21 divided by 25, basically, because these two guys cancel out, and you get
0.84.
0.84 mole per decimeter cube.
Okay.
And can you please again tell that what is titration?
Titration is a technique. Titration is a technique which is used when you are reacting an aqueous acid with an aqueous base, also known as an alkali. Okay.
Yes.
All right. So you add the acid to the burette, you add the acid to the conical flask using a pipette, and then you slowly add the acid to the alkali, and right, you see where you end up.
Okay.
So okay, what have they done here? Ah, that's what they've done. I should warn you. I'll show you the book, And I show this as a warning because, obviously when I'm looking at it, and I need to be careful as well. It will confuse me. And so we initially calculated, you can see that there are errors over here, right? Over here they're dividing it by 1,000. Over here they're dividing it by 10,000.
Yeah.
Right. So if we just do the calculation that we did, I was relying on the book, but let me just do it myself if we haven't made a mistake. So 21 divided by 1,000 into 0.1, which is 0.0021, which is 2.1 into 10 to the, yeah, see, there you go. There's the mistake, right? So the book is saying that it's 21 into 10 to the power minus 9, and I just relied on that. It's not 21 into 10 to the power minus 3, it is 2.1 into 10 to the power minus 3. Right, I'll show you the other mistakes. Well, technically not a mistake, but that's the mistake over there. Over here they've done it correct. So what you're actually going to get up is 0.084 moles, not 0.84, 0.084. So
Yeah.
yeah, so I'll take you back to the whiteboard and make that correction. And so be careful when you, like, the book has mistakes,
Yeah.
right? All right, can you see the whiteboard?
Yeah.
Okay, now to avoid confusion, right, the calculation, like the steps that we did are correct, just the value is wrong, so I'm just correcting the value over here. So this is 2.1 into 10 to the power minus 3, right? Putting a decimal over here will solve that problem. And so over here it's 2.1, and so that will give me 0.084, not 0.84, 0.084 mole per decimeter cube.
Sir,
Yes,
in this formula, we have the fixed volume of 24 decimeter cube.
that's for gases.
Okay.
We're dealing with solutions. Right now, to make life easier, there's like a general formula that you can use for titrations. Right? That would be helpful, wouldn't it?
Yeah.
And so the general formula for titrations, I'll write that out in black. So it's C1 V1 over M acid, well, I mean M1, right? And this is for the, like, acid or alkali, whatever you want, equals to C2 V2 over M2, where C is the concentration, V is the volume, right, used in centimeter cube.
Okay.
And M is the number of moles, right? Number of moles in the chemical equation.
So titration is the same as stoichiometry.
Titration uses stoichiometry. It's not the same thing,
Okay.
right? And so one could be either the acid or the alkali, and so two would be the other thing. So if we plug in these values, for example, we had the acid, and so that was 0.1 times 21, and the number of moles in the chemical equation was 1. equals to, we don't know the concentration, so that's X times 25, and the number of moles was also 1. Right, so basically X equals to 0.1 times 21 over 25. Do we get the same value? Sophia?
Yeah.
0.1 times 21
Just a
divided
second.
by 25, and we get 0.084. And because X is the concentration, so that would be moles per decimeter cube.
Yeah.
Didn't
Yeah.
that make life much easier?
Yeah.
Right, remember concentration, volume in centimeter cube, and moles of the chemical equation, not the number of moles that you, like what we did over here. Right, moles of the chemical equation, so the mole ratio is important.
Volume can be given in centimeter cube as well.
For this, otherwise, right, separately, when not doing titration, you need to convert the volume into decimeter cube.
So we have to divide by 1000.
1000, yes, which we did over here, remember?
Yeah.
Right, so this is a useful, right? So one would be, whatever you know all the values for possibly, and the other is where you have the unknown, right? One is the acid, the other is the alkali. That's up to you which one you put where. You're bound to get the same answer. So to, cement this concept, I am going to do another example.
It can be alcohol as well.
It can be what?
Alcohol or alkaline.
No, titration is between acid and alkali.
Okay.
Alcohols are, well, first of all, there's organic, and they don't have this property. So,
Okay.
right? So, question, your the unknown can be for the alkali as well, right? So, in fact, for the acid. So, this one, the unknown concentration was for the alkali. The unknown can be for the acid as well. And I think that's what we're doing right now. So, you're conducting a titration of sulfuric acid with sodium hydroxide. Right, so you've got H2SO4, which is sulfuric acid, and you are using 25 so that's sort of like the standard. It could be anything. 25 centimeter cube of sodium hydroxide. Then you've got sulfuric acid. Then you've got sodium hydroxide, and you have used 20.15 centimeter cube, and the concentration is 0.2 mole per decimeter cube. Right? So what we want
Yeah.
is the concentration of sulfuric acid. So the first thing we want is the balanced equation. So H2SO4 plus NaOH will give you Na2SO4, right? And H2O. And it needs to be balanced. Shobhi, would you like to balance this?
Um. Do I have a choice?
Not really, no.
Then
Adam, you can try as well, obviously.
let me see. The first thing, the H is balanced. Wait,
H is not balanced.
two. But two. It has two here and two there.
No, 2 and 1, 3. And over
Oh
it only
yeah.
has 2.
Yeah.
Oxygen is balanced, sulfur is balanced.
Yeah.
Hydrogen and sodium are not balanced.
We gotta put two
Where?
on the near the sodium.
Which sodium? The NaOH?
Yeah. Yeah.
Okay. And so that balances the sodium. And how many hydrogens do we have now? We've got 2 hydrogens here, 2 hydrogens here. That makes it 4. We only have 2 hydrogens here.
You gotta put 2 there.
And so that gives us 4 hydrogens, 2 oxygens, and 2 oxygens. Now it's balanced. And so you got a mole ratio of 1:2. We're not concerned with these guys because the reaction's happening between the sulfuric acid and the sodium hydroxide. So
Yeah.
the ratio is 1:2. And so remember C1 V1 over M1. So C1 V1 over M1 equals to C2 V2 over M2. Right? And so what that gives you is, right, let's take one as sulfuric acid. So the concentration is unknown. So that's X multiplied by 25 centimeter cube over how many moles do we have? 1, right? In the equation. And then you
Yeah.
have, right, the concentration of sodium hydroxide. So that's 0.2 times the volume, which is 20.15 in centimeter cubes. And the number of moles over here in the equation is 2. Right? And therefore, X equals to 0.2 times 20.15 divided by 2, and the whole thing divided by 25. Right?
Yeah.
What are we
Yeah.
getting?
Just a minute.
So 0.2
0.2.
multiplied by 20.15 divided by 2 divided by 25.
0.03.
0.0806.
Yeah, so if we round that up, 0.0806, we can say 0.081
Yeah.
moles
Yeah.
per decimeter cube, right? Because normally you want your answer to 2 significant figures, right? So this is the 2 significant figures,
Yeah.
okay? And so that is the concentration of the sulfuric acid that you have used in the titration. Now, just to show you from the book, this was a work example. And so just to show you that they actually went the long way that we did initially. And so you can see they found the number of moles of sodium hydroxide that were used, right? Not from the equation, but actual number of moles. And then they used the mole ratio to find the number of moles of sulfuric acid. And then they used the number of moles of sulfuric acid to find the concentration, which is also correct, right? So you can do that, and in fact, depends on the question. It depends on how the question is asking you to solve it. So you can do it directly this way, but if the question is given to you in steps, they're like, okay, fine, calculate the number of moles of sodium hydroxide in the volume that was used for titration. So 20.15 centimeter cube, how many moles of sodium hydroxide were used? And so you calculate that and you get 4.03 into 10 to the power minus 3. And then like, okay, fine, how many more? And then they ask you to use that information to find the concentration of sulfuric acid. And so how can you do that? So you need the balanced equation. And so you take half because, right, the ratio is 2:1. So you take half of that, so you divide by 2. You get 2.015 into 10 to the minus 3. So 25 centimeter cube of sulfuric acid contained half the number of moles as compared to sodium hydroxide. And then you apply the formula for concentration, right? Which is number of moles divided by volume, and you get 0.081. So whether you use, like, this is given differently, but it's what I told you, they've given you all of this. The reason I didn't tell it to you this way is because the M and the N can be confusing. So instead of M being used for concentration I've used C. It doesn't matter, right? It's the same thing. Whether they've given like whether they're expecting you to solve it step by step this way, or whether you can go ahead and just do it directly this way, it depends on how the question has been framed and what they're expecting you to do. Right. So with this, right, hopefully the concept titration is clear, and we'll do questions in the past papers, and that will help as well. And we are officially done with the syllabus for chemistry as well. Congratulations. So
Oh,
yes,
okay.
yes, we are done with chemistry as well. Alhamdulillah. And
We're
so the next time we will be
gonna start with past
we are
papers.
going to start with past papers inshallah.
Okay.
Right? Both chemistry and today was supposed to be physics, but we're doing chemistry since it's you guys in both classes. So yeah, okay.
Okay. Okay.
So I will see you next time inshallah, and we'll be starting off with password practice.
Allah Hafiz.
Okay.
All right.
Allah Hafiz.
Allah.